Hello! So, in this video, we're going to talk about cameras. So, in the real world, a camera is an object, like say, your eye, that takes rays of light coming into it, and then it turns them into a picture. Now, if you remember back to the first episode, I said that we did ray tracing sort of in reverse, in that, in ray tracing, the camera is not an object that receives and detects rays, but it sends them out into the world to sort of probe it and see what it's like. Now, this means that our camera is not an object that needs to actually intersect with rays. Instead, it's an object that produces rays. So, we need some way of understanding how real cameras convert rays into images, and then we need to reverse this process. So, in the real world, the principle of pinhole cameras is used, as far as I'm aware, totally exclusively. So, eyes use this principle, as do cameras, both modern and early cameras. So, the idea is we have some sort of detector, and then we have a screen with a tiny little hole in. So, and this is all in a box. So rays of light can only enter through this hole. Any light ray coming in goes through this little hole. Which means on the detector, we now have very specific points corresponding to directions of light. And this is how you get a clear image. You sort of, each point on the detector only sees one very specific point in the real world, which is along that ray. So we can reverse this. So one important thing to note before we continue is that this will actually generate the image upside down. So if we have a little stick man here, you see this lowest point at the bottom actually goes to the top of the detector, and this middle one goes to the middle of the man. So you get something looking like this. Now, we would, in digital cameras, flip this upside down. In cameras with photographic plate, you can just flip it around. So this isn't a problem at all, but we do need to be aware of it, or we'll have all of our images the wrong way round. So if we try to replicate this by sending things out, so we can take up some physical space, and we can pick points on this, on a plane, a little small rectangular surface we have here, and then give them the direction to go at that point, and just keep them going. And then we don't need to worry about this screen, because we're only detecting rays going to that point. So we don't actually need the physical parts of this detector. But there's a neater way to do this. Because here we have to worry about flipping the image round. But if we extend this box over, and we imagine that we have another surface here. Now, this isn't a physical surface that rays can hit. It's just something we're going to imagine to help us generate cameras. We can keep these rays going. And in fact, all the rays will pass through this center point and hit this surface. But what's neat is that if we have the image detected on this surface instead, then it's the right way up. We don't need to worry about it being upside down. Now, this wouldn't work in reality, because you're not able to filter the light out first. But we don't need to do that, because we're producing the rays. So any others that might hit our detector, as far as we're concerned, don't exist. Because we can just choose not to create them. So actually we can get rid of this whole part of the diagram. And this now gives us a much neater way of representing the camera. So we have its center point here. And now, even in pinhole cameras, this is where it looks like the image is being taken from. The pinhole, not the detector. So, by actually making this the point we care about, it makes it much more intuitive to see how the scene is built up from our given camera. And now if we can describe this surface, which isn't a physical surface, I want to emphasize that point, it's imaginary, to be used for creating the rays. If we can also describe this surface and how points on the image we want to produce correspond to points on this surface, then all we need to do is take the ray that goes from the origin to the relevant point on the surface, and that then is the ray for that part of the image. So when we want to do this, there are lots of things we need to consider. So describing the surface that we want the rays to go through, there are several things we need to consider. So if we have this surface, one way to generate points on the surface is we start with a center point. And from this point, if we have two vectors, a right vector and an up vector, we can now just add together multiples of these two vectors to get any point on this surface. Now we're going to assume that these are normal vectors, so they each have length 1. Now this means we need to consider the height and the width of this surface, because these are going to be the maximum multiples of these two vectors that we can use. And notice we choose this center point as the origin. Effectively, this is the 0 point. And we do this because if we have the camera looking at the surface, we can have a forward vector. And this will then take us to that very center point. And so actually, the direction we want, the correct direction vector, can just be made by taking that forward vector and then adding on the correct multiples of our up and right vectors to move on to the right point of that surface. So just by using multiples of up and right and adding on forward, we have the direction we need, which is great. But we need to think about what multiples we use. So generally in computers, an image is represented by a big grid of pixels. And what's a little awkward here is that 0 is up here in the top left. It's not in the center. And ultimately, we're going to want pixels in a grid rather than vectors. So we need to be able to convert between these two formats. And also, this is in pixel width and pixel height. And our surface is not using those same measurements. Our surface is using some sort of spatial measurements in our world. And it's really awkward to convert between the two, because there are other factors rather than just the size of the image that matter here. So first of all, we may want to increase the pixel count, but use the same image plane to get just a higher resolution version of exactly the same thing. But changing the size of the image plane is the same as zooming in or zooming out. So they're not directly connected. So let's think about how we actually get the right size of the image plane. So there are two pieces of information we need for this. We need the field of view, or shortened to FOV, and we need the aspect ratio. So the aspect ratio we can calculate from the pixel width and pixel height. So it's just the width divided by the height. Sometimes it's written in other ways or the other way round, but this version of the aspect ratio is going to make our equations the neatest. And now we also need to know the field of view. So again, there are several ways of describing what it might be that will give you different results, but in this video we're going to consider it if this is vertical, so this is y up here, this is the field of view, this angle here. So bear in mind that the screen still goes below, but we only consider part of this field of view. And we're also going to measure the height in a slightly funny way. So this is 0, this is height, and this is negative height. So the actual height of the screen is 2 times h, which seems odd, but doing it this way will make the equations neater in the end, I promise. And so we will be given the field of view. The field of view is part of describing the camera. So a really small angle is similar to being really, really zoomed in, and a really big angle is similar to being zoomed way, way out. And as you get close to a right angle, you get this sort of fisheye effect that you might have seen before. Bear in mind that you can't increase the FOV beyond 90, and you can't make it negative either. And so now we have this field of view, we can actually go ahead and we can calculate the height of our image plane. So if we just take part of this image and not the whole thing, we get ourselves a right-angled triangle. Now, it would be really helpful if we knew the length of either this side or this side. So let's just imagine that this side has length 1. Now, what this represents is our forward vector. So as long as we ensure that our forward vector is normalized, that is, that it has length 1, this model still works. So we have to be careful with that, but otherwise it's fine. And now once we've done this, we can use a bit of trigonometry. So this gives us that the field of view is equal to the tangent of h divided by 1, which is just the tangent of h. And now, reversing this, we get h is the inverse tangent of the field of view. Wonderful, we've got the height of our surface here. But we also need the width. Now, we want it to match the dimensions of the pixel. That is, we want its width and height to have the same aspect ratio. Otherwise the image will look stretched, and we don't want to have to do that. And we set up here, the aspect ratio is the width divided by the height. So the width is just the ratio times the height. So this is really good. We can now describe the width and the height of our sort of imaginary image plane that's floating 1 unit in front of the camera. And so now we have this surface, which I'll draw out a bit bigger here. So this is the point 0, 0. This is our up vector. This is our right vector, which we will worry about calculating later. For the moment we can just assume they're part of the definition of the camera. But notice that I said, well, h is up here and negative h is down here. So in a way its height is twice that, and that means that our width is over here, and our negative width is over here. So actually its width and height are twice what our h and w are. But this means that if we have, say, alpha u plus beta r to represent a point on the surface, alpha can vary from negative h to h, and beta can vary from negative w to w. And now we've got these ranges that alpha and beta can vary between. That's really helpful for converting between the pixel image and this floating screen in the middle of nowhere. If we're not too worried about converting straight back to pixels, we can already describe the rays. So as long as we're happy with a funny coordinate system that goes from -1 to 1, then we can describe any vector as our forward vector plus h times y times up plus w times x times right. Now, this is where x and y vary between -1 and 1, which is a slightly unusual coordinate system. But this is sort of taking hy and saying this is alpha, and taking wx and saying that's beta. And it still varies in the correct ranges, from alpha being negative h to h and beta being negative w to w, because x and y vary from -1 to 1. But what's nice here is we don't need to care anymore about anything specific about this image. By choosing y and x, we can then get the right ray. And y and x always vary from -1 to 1. There's no longer anything specific about our screen in doing this conversion anymore. So now all we need to do is take a pixel grid that goes from 0 to some, let's call it pixel width and pixel height. And now we need to convert this into -1s to 1, a sort of x and y in here. So if we have our pixel x, this varies from 0 to pw. So first let's get it to vary from 0 to 2. Now the reason we do this is because the difference between the smallest and the biggest possible values in our target range is 2, from -1 to 1. So if we can get this varying from 0 to 2, then all we need to do is offset it a little. So to do that, we want to take twice px and divide it by pw. And this value here varies from 0 to 2. And now all we do is subtract 1 off this. This value varies from -1 to 1. So we can say our x equals this, and we will plug that x into the above formula, and we'll get the right horizontal value. We need to do the same thing with y, and it's exactly the same thing. Twice the pixel y, divide by the pixel h value, and subtract 1. And there we go. We've found a way to convert from a pixel grid onto this floating screen in the middle of nowhere, and then we can use this equation up here to get the direction of the ray. Bear in mind that we will need to normalize the result of this equation to make it length 1. And we already know the origin of the ray. It's the origin of the camera. So we have everything we need to generate rays. So now I'll talk about how we actually produce a camera in code. So we could give it all of the pieces of information we've talked about. We can give it a forward vector, a right vector, an up vector, an origin, an aspect ratio, a field of view. But I mean, that's a lot of information to give it, a lot of data points to pass in. And not only that, but a lot of these satisfy very specific constraints. The forward, right, and up vectors actually all have to be perpendicular to each other. And so we can't just take anything in. And so we'll use a method that takes less information in and is a bit easier to use, and will produce a valid camera for a much larger range of possible inputs. So we still need to take a field of view in, and this still has to be within the range 0 to 90. But then instead of taking forward, right, and up, we'll take a target and an up, or rather an up guide. We'll get onto why this is only a guide later. And so this gives the camera a point that it's looking at. And now, I think this is a bit easier to work with, because if you have a focus of your scene, then all you need to do is set the target point to be that focus, or a point around it, and then everything else is sorted. You don't need to worry about finding the correct directions and which the right is. We still need an up, but this is only a guide, so we can just set this to be the what we consider to be up, the opposite direction to gravity, and then we can sort of use this method we're about to go through to actually get the correct up vector. And we'll also need the ratio. If we're just going to pass in values from -1 to 1 into our camera, then we will need that ratio. And finally, we'll need the origin. We do still need the start point. But now we have all this information, we can actually go and get our forward, right, and up vectors, which seem to be missing. So our forward vector is just going to be the target minus the origin. So this is the vector that goes from the origin to the target. But we do need to normalize this result. We need to make sure its length is 1. And now we can use the cross product to get all the other parts we need. So our right vector is going to be the forward vector crossed with our up guide. So it's important to make sure we get the cross product the right way round, or this would end up being a left vector instead, and the whole image would be mirrored. But now finally we can get the actual up vector from right cross forward. Now the good thing about doing it this way is that these vectors are now guaranteed to be at right angles to each other, though we do still need to normalize them. So now we have a way to take an image and then take the pixels in that image and convert them into rays that we can fire into our scene. And then using information about the ray, we'll later be able to get the correct color for that pixel, and that's how we're going to build up an image. So in the next episode, we will go over the code for this, and we will use that to generate our first image. So, thanks for watching, and goodbye.